This is section 13.6, and we are finally at the end of our notes for this particular section. We're going to do one last problem on surface integrals over a vector field, or in other words, we're going to find the flux of this particular vector field over the unit sphere. And then we have some hints here because we're going to have some fairly ugly integrals that we're going to get out of all of this. So let's start with finding the vector equation for the sphere. We did this earlier in our section here, and we're gonna use phi and theta to get, and this is a radius of 1, so we have sine of phi, cosine theta for x, and sine of phi and sine theta for y, and then cosine phi for z. So again, that vector is representative of our unit sphere. And then we're going to take the partial derivatives here to set up our cross product. So we're going to get a cosine phi, cosine theta, cosine phi, sine theta, and negative sine phi. And then we'll do the same with theta. So we get negative sine of phi, sine theta, and sine phi and cosine theta, and then 0. Okay, we're going to set up the cross product. So I'm going to pause and write out this portion. Okay, so I've set up the cross product between these two vectors and perform the cross product. Obviously the cross product is a bit ugly, so what we can do, we can't really do much with these first two components, but what we can do is simplify the last one, which will help us a little bit. Remember, while you're working on these problems, especially if they're kind of ugly problems, you want to make sure to simplify as much as possible before going on to the next step. In this case, if you think about the last component, cosine squared plus sine squared is equal to 1, and we're able to factor out the cosine phi, sine phi. So, and we've done that for a number of these examples in this section. But anyway, here's our cross product. So we'll hold on to that for a moment. Next, what we'll do is take a look at our vector f, which is made up of x, y, and z, and we're going to substitute in now r of phi theta. So again, in other words, what we're doing here is we're taking z, which is the first component of vector f, and we're going to put in component 3, component for z, in our equation for the surface. So we're going to put in cosine phi for z for our first component. So we have cosine phi. Then what we're going to do is take our next component, which is y, and we're going to put in our component for y, which is going to be sine of phi, sine of theta. And then our last one is x, which is sine of phi, cosine theta. So again, that's going to be our vector f now written in terms of vector r. Okay, our next task is to come up with the integrand of our integral. And the integrand is going to be the cross product between these two vectors we just found here. So let's go ahead and work on those. If we take the vector for f that we just developed, all right, so if we do the dot product here, what we get is, oh, and I noticed that I just missed an angle here. Hold on. So this is sine squared of phi. Oh, and I just noticed that I missed it up here as well. I apologize. So this is going to be sine squared of phi. All right. Okay, so back down here we have sine squared phi. And again, we're just multiplying these components together. And then cosine phi and cosine theta. A lot to keep track of here. Okay, the next one is plus sine cubed phi sine squared theta. And for our last one, we have sine squared phi, cosine phi, and then cosine theta. All right, now if you notice, we do have two of these, so we could group those together. And we finally have our integrand to the double integral. And it's not a very pretty one, but we have some formulas that will save us some time. Okay, so I'm going to go down to the bottom here. I'm going to skip through the answers in the notes, and then we'll go ahead and write out the double integral. So I'm going to pause. All right, so our variables of integration is going to be, I'm just going to do d phi d theta, which means that if we're thinking about an entire sphere, think the whole thing, the theta measurement will be from 0 to 2 pi, and then the phi will be from 0 to pi. So this is our double integral. Now, remember, we can split this up, which is going to save us a little bit of time. So, for instance, we could do the integral from 0 to pi of 2 sine squared phi cosine phi d phi, and then we have times the integral from 0 to 2 pi of cosine theta d theta. So that would be just this first portion of integrand. We can split this one off because of the addition, and because it's separated by multiplication, we can split up the integrals. So that would be the first first portion there, plus, and then what we could do is sort of a similar thing here and take sine cubed of phi d phi and multiply it by 0 to 2 pi of sine squared theta d theta. Now, remember, we worked on this a lot in class, especially in chapter 12, where we were talking about all this integration. This particular integral is one of those special ones where we can use our kind of shortcut technique here. Cosine looks like this from 0 to 2 pi. And if you guys remember, that's 1, that is 1, and this is 2, which means that what we get here is 0. And that's great. I don't even care about this one anymore because that whole thing is 0. So anyway, that saves us a little bit of time at least. Okay, now what we're going to do is we're going to tackle the rest of it. So the remaining portion of this, we're going to split up. Now we do have our formulas, and these are given to us in our notes. So for the sine cubed, we have negative 1/3 times the quantity 2 plus sine squared phi times cosine phi, and we're evaluating that from 0 to pi, so that's that one, times, and then sine squared, we've done that one a few times, that's 1/2 theta minus 1/4 sine of 2 theta, and that one we are going to evaluate from 0 to 2 pi. So for our first one, what we get if we plug in pi, sine of pi is 0, cosine of pi is -1, so we get positive 2/3 minus, and if we plug in 0, sine of 0 is 0, cosine of 0 is 1, so we get -2/3, that's going to be plus 2/3. So for that first one, we get 4/3 times, and if we plug in 2 pi, we just get pi, sine of 2 pi and sine of 0 is 0. And we finally get our answer of 4 pi over 3. Okay, this concludes section 13.6.